By looking at the problem, I did not get it was a topological sort, but when there was this condition that something has to be before others. So when we need some linear ordering, I needed. This was the major point when I realized it was a topological sort question. That linear ordering is required and sum above is always before below, which means it is a u comma v linear ordering wherein always this u should be before v. And we know that if any matrix is present in the answer, then we need to return it. In the sense, there can be a case where no answer exists. So this is when it is possible, when cyclic behavior is present, right? We know from the topological sort. So now the first thing was like I did not know how to implement the TopoSort. So I used some parent-child relationship arrays and another version of DSU to replicate this kind of behavior, but it wasted so much of time. So we'll directly go to why it works. Now it is just given that we have a particular matrix that needs to be formed and we have some conditions that something should be before something. So for each row as well as column, we will have separate linear orderings of its own. So TopoSort of row, this will be TopoSort of row, and then TopoSort of column, this will be one linear ordering, say 1, and this will be 2. Now using this 1 and 2, we need to form the matrix. Now to form the matrix, what we can do is, now suppose over here the linear ordering comes out to be say 1 3 2 for the rows, and then if it comes out to be something like 3 2 1 for the columns. Now what does this mean? It means that 1 comma 3 comma 2, 1 should always be on top, so it should be in the 0th position somewhere over here, somewhere in this line, right? And then similarly 3 should be somewhere in first line, 1 should be somewhere over here, and 2 should be somewhere over here. So now as we can see, there can be multiple answers, right? Multiple correct answers can be present, we know that. So 3 can be either here, or even 3 and 1 can be replaced also. Over here 3 and 1 can be replaced. We just need that 3 should be before 2 inside the columns, right? So we can also write that 3 is here and then 1 is over here. This also satisfies, right? If we have 0 over here and 0 over here, right? Now what we have is 1 3 2 1 3 2, column is satisfied. 3 2 1 3 2 1. This rows and both columns are satisfied, linear orderings. Now to get the linear ordering, this was the only major point in the question, that to get the linear ordering you have to make a graph out of it and then just pass on that graph to a TopoSort function, and then let the TopoSort function give you that TopoSort linear ordering, which we will use to make the matrix. Now directly we can go ahead and look at the code itself. So the main thing is we'll be building the matrix itself, right? So when we are building the matrix, first what we are doing over here is we are just declaring a graph. So this is my first graph that I am making. So this part is for the row section, right? Making the graph, create graph. What I am doing, I am creating a graph. I took an adjacency list. I took a k plus 1 because here in the question it was given that it has 1 plus k, right? In the sense from 1 to k, 1 based indexing was there. So I took a k plus 1 just in case. And then I just created the graph normally how we do that from U to V wala pair. It is a directed one. Now second thing is I just topo sorted it. Now if I know that topo sort was not possible in that, which means that there is no possibility if topo sort is not valid, so I'll just return a empty. Similarly, for similar steps I have done over here. For this was for the row, this is for the column. Now what I'm considering is in this TopoSort function is this I had to write, we'll go through it again, but apart from that we just know that if there is, we have the TopoSorts. So now if I have 1 3 2, I just need to make sure that this 1 2 1 3 and 2 are in the correct rows right now. Now I just need to make sure this 1 goes on to a correct column, 3 goes on to a correct column. Now the editorial that they have done, now I have these two things, right? Now in the editorial they have given that what they are doing is they are going from int I from 0 to k, and then for j again from 0 to k, and they are considering that if the column, right, the column sort of I is equal to row sort of j, then we are perfectly sure that our answer of ij will be equal to either column sort or row sort, because it is the same thing. So this is what the editorial is. I did not come up with this, the Leetcode editorial had this. This is very good actually. So what we are doing is we have 1 3 2 and then 3 2 1. We are going to traverse each and every one of it, and then over here when we come it is like 0 0. Now we'll see it is 1 over here, but it is 3 over here, so this is not populated. When we come to here it is 1 0 1. Now 1, this cannot be populated. Over here we come 0 2, 0 is 1, over here 1. Now we see that it is matching. This is a what we'll call intersection of those values. Then we can just put 1 over here. Why does this work? This works because what we are ideally doing is we are placing that particular element according to its row also and according to its column also. The same thing we can also do. The same code, what I had done was I had taken a map so that I'll just store the indexes of these. So 3 comes at 0, this is my map. 2 comes at 1, 1 comes at 2, this is my map. So now as soon as I go to 1, right, over here I'm going to just iterate over these and I'll just do n updations. So from my O of n square, this boils down to O of n, but space complexity increases from O of 1 to O of n. So this was the trade-off that I did, and I got this only in mind. I could not come up with this genius solution of O of n square, like I did not get this in mind. So now from 3 to 0, 2 to 1 and 1 to 2 we have in the map. Now we just say that from when we are at 1, right, over here we are at 1, in the sense at 0 index, the 0 1 2 indexes, this is the indexes and this is the values. Now at 0 index we know that it is 1. Now what we are saying is wherever take the column index of 1. So now we know that 1 is at 2. So the j we found out what the j had to be. So I comma j, I'll just insert it, which will be equal to my either this or else this, anything I can take. So I just updated it. I just updated one. In single shot I updated one. I did not go through this and then updated. That was the only difference that I had followed from the Leetcode editorial. You can just take a look at the topological sort also, the code for topological sort. It is basically Kahn's algorithm that I've used over here. Over here it is just a BFS implementation of the TopoSort. BFS implementation is, we take in degrees, push all the elements with in degree, first calculate this, then second point is in degree equal to 0, just push it in the queue, iterate over till queue is empty. Just iterate over it and see if any further, go to this point, any further neighbor in degrees become 0. Neighbor in degree equal to 0 after removing contribution of in degree from parent. This is the third point. Then fourth is just, normally after doing this we will have some answer set of our TopoSort. Now we just need to check if this answer set's size is equal to k, or else the number of vertices. If it is, then valid or invalid. If it is not equal to, then it is not valid TopoSort. If it is not valid, we are just returning a normal empty array. If it is valid, then we are going ahead and creating the proper matrix. So this was it. This was a hard problem, ideally, but anybody who has experience of TopoSort and doing TopoSort, I did not have much experience. I did not practice also, so that is why I took some time and I strayed off. But yeah, I hope any next question in the future I'll be able to tackle in a better way. That's it. Thank you.